and will be followed by a 15-minute Q&A session. Whenever you have a question, even during the presentation, please type it in online and we'll answer it during the Q&A. Your presenters are Deepak Bopanna, Lattice Semiconductor's Senior Director of Marketing, and Gordon Hands, the company's Marketing Director for IP and Solutions. And at this time, I'd like to turn the microphone over to Deepak to begin the presentation. Deepak?
Thanks, Brian. Hello, everyone, and thank you for joining us for this webcast today. I'm Deepak Bopanna, Senior Director of Product and Segment Marketing at Lattice, and co-presenting with me today is my colleague Gordon Hands, Director of Solutions Marketing at Lattice. I'm going to kick off things here with an overview of the rapidly emerging edge computing trend, share a few examples of always-on, on-device AI applications and their unique requirements, and highlight how low-power FPGAs can be used to address system-level performance and power consumption trade-offs to achieve flexible and scalable on-device AI solutions. I will then turn the presentation over to Gordon, who's going to focus on chip-level optimizations and illustrate why a couple of common on-device AI use cases, such as face detection and human presence detection, how design factors, including on-chip FPGA resources, network size, quantization, etc., impact key product attributes. Lastly, we've also included a few poll questions at various points in the presentation, and we look forward to your participation to make it more interactive. Edge computing, or intelligence at the edge, is being driven by requirements such as latency, privacy, and bandwidth limitations. Some edge devices, such as autonomous robots and drones, for example, cannot afford the latency involved in cloud-based AI and need on-device processing of the sensor data for collision avoidance. Privacy is another concern, as sending data over a network to the cloud exposes it to potential hacks as opposed to on-device processing. Along the same lines, even with 5G on the horizon, sending all the video data generated by surveillance cameras back to the cloud, for example, will hog the networks, as opposed to performing on-device AI and only sending the video frames of interest to the cloud for advanced analytics. Cloud-based AI will continue to be required, but will be complemented with on-device AI in many applications. Always-on, on-device AI is an increasing requirement in many edge applications, such as smart home, smart city, and smart factory. Human presence detection, for example, is a common use case in many context-aware applications, such as smart home appliances or vending machines that turn on the display only when required, or smart doorbells that ring automatically when a package is delivered, or home surveillance cameras that send alerts when an intruder is detected, or consumer electronics such as TVs that turn off when no one is present for a while. Other examples as shown on the slide include smart speakers or any voice-controlled appliances that need to be always on to detect key phrases, or retail store cameras that track or count people in the store, or toll gate cameras that perform vehicle classification, or machine vision cameras that count objects or check for defects as the product goes by on the conveyor belt. Many of the edge devices that require always-on, on-device AI functionality are either battery-operated or have stringent thermal requirements. Additionally, such devices are compact in size and also ship in high volume. As a result, designers typically like to minimize the power consumption, cost, and board area for including the on-device AI functionality. Similarly, designers typically prefer to reuse as much of the existing non-AI design as possible, including sensors and other legacy devices on the board. As such, the AI accelerator needs to have flexible interface support to seamlessly integrate into the existing design, in addition to flexibility to support evolving AI algorithms and architectures. Last but not the least, designers want to customize the performance and accuracy of their on-device AI solution instead of a one-size-fits-all solution that may be an overkill for their application. The combination of these requirements demands an ultra-low power, scalable, and flexible inferencing platform optimized to minimize cost and board space. It's time actually now for our first poll. So please take a few seconds to share your number one requirement or priority for your AI design. As we talked about, minimizing power consumption is important. In some cases, board area, as well as flexibility, both from a interfaces and evolving AI algorithm support. So it'll be great to know your view on this. All right, so looking at the results, majority of you answered flexibility is your number one priority, followed closely by minimizing power consumption. So that's good to see. Moving forward, to help address the unmet need in the market, Lattice launched the Sense AI Stack, a complete technology stack optimized for flexible on-device AI. Solutions based on the stack only consume from under 1 milliwatt to 1 watt of power are offered in small packages ranging from 5.5 to 100 millimeters square and are customizable for performance and accuracy with 1, 8, or 16 bits quantization support. The Sense AI Stack includes all the building blocks required to rapidly design flexible inferencing solutions, including modular hardware platforms with onboard sensors, parameterizable CNN accelerator soft IP cores, neural network compiler tool to interface with industry standard frameworks such as Caffe and TensorFlow, reference designs and demos for common AI use cases such as face detection, key phrase detection, object counting, as well as an ecosystem of design service partners to deliver custom solutions across a variety of applications. System architects have a variety of programmable options to implement on-device AI, including MPUs, GPUs, and high-end FPGAs that provide high performance, but also consume high power that may be prohibitive for many always-on edge applications. Similarly, MCUs consume relatively lower power, but lack the performance required in many embedded vision applications, for example. Lattice FPGAs that are part of the Sense AI stack, such as the ICE40 Ultra Plus FPGA and ECP5 FPGA, are optimized for low power, small size, and cost, and can be used to implement flexible inferencing solutions from under 1 milliwatt to 1 watt, as shown on this slide. The highly parallel nature of the neural network inferencing functionality maps extremely well to these FPGAs, making them an ideal choice for either standalone implementation or when used in conjunction with other programmable devices. Some always-on edge devices, such as smart doorbells, for example, have stringent space requirements. System designers typically prefer fully integrated solutions that directly interface to the sensor, perform on-device AI processing, and take necessary action as required with low latency. The ICE40 Ultra Plus FPGA, for example, can perform human presence detection or gesture detection with no other external devices required other than the sensor, and comes in packages as small as 5.5 millimeters square. The ECP5 FPGA family can provide scalable performance with multiple CNN accelerator cores that can fit into 25, 45, or 85,000 lookup tables in package sizes as small as 10 by 10 millimeters square. Certain always-on edge devices, such as surveillance cameras, may require advanced analytics, such as face recognition, to be performed by a high-end ASIC or ASSP. In such cases, system designers have to balance the required performance with the available power consumption budget, as operating the high-end ASIC ASSP in always-on mode is going to consume significant power. A viable architecture could be using a combination of ultra-low power FPGA as an activity gate that performs always-on face detection and wakes up the high-end ASIC or ASSP to perform face recognition only when required. This concept can also be extended to hybrid edge cloud scenarios where the advanced analytics is performed in the cloud based on the useful video frames identified by the edge device. Lastly, in certain cases, system designers may be looking to add AI-enabled embedded vision intelligence to edge devices that may currently be operating only on simple MCUs. In such cases, rather than upgrade the MCU to a more powerful processor, it may be easier to seamlessly add a low-power FPGA coprocessor that can interface with the image sensor as well as the legacy MCU and perform the required inferencing functionality in a scalable manner. The MCU can continue operating as the control processor, including performing system control based on the result of the inferencing provided by the FPGA. Now it's time for our poll number 2. Please take a few seconds to select which of these system architectures may be applicable to your design. As we looked at, there's a standalone integrated FPGA for space-constrained applications. In some cases, you can use FPGA as the activity gate to wake up an ASIC or ASSP for advanced analytics. Or in some cases, you can seamlessly use an FPGA as a coprocessor to low-end MCUs. Please share your view on this. Right, so the majority of the responses, FPGA as a coprocessor to MCU could be the most applicable, followed by the standalone integrated FPGA. That's good to know. Thank you for your inputs. So at this point, I'm actually going to hand it over to my colleague, Gordon Hans, for the rest of the presentation.
Okay, and thanks, Deepak. So we're going to switch gears a little bit and look at what kind of functions can be placed inside a small low-power FPGA. And I wanted to start just by briefly reviewing the design flow that we have for the Lattice products. And this diagram is really split into 2 different portions. So the top portion is the machine learning portion. And here at Lattice, we're pretty excited that this part of the flow requires no understanding of VHDL or Verilog. You simply complete your machine learning design using either TensorFlow or Caffe, and then compile for implementation by one of our CNN accelerator IPs. The bottom portion of the diagram shows a more traditional FPGA flow, and here designers combine one of our CNN accelerator soft IP cores with the various different system interfaces and other logic they require to create a bit stream that can be programmed inside the FPGA. So let's take a quick look at what sits inside some of those soft IPs. We have 2. The first that I'm showing is what we refer to as our CNN accelerator IP. This would be used with the Lattice ECP5 devices. So let's take a quick walk through the diagram. On the left-hand side, we have a AXI bus, which connects to a DRAM. And then that DRAM is being utilized really to store a variety of things. So it can store the instructions that are required to run the engine, the weights associated with the network, and any intermediate data values that can't be stored using their local on-chip memory. In the upper left, we have the command queue and a state machine that controls the engine. And then in the center, we can see the actual engine. It's referred to as the engine pool here. This has the various components required to process different aspects of a CNN network. So I show a few of them here: convolution, FC for fully connected, and pooling. And then on the right-hand side, we have the local memory pool that is used to store intermediate values as we go through processing. So this second diagram shows the block diagram of what we refer to as our CNN compact accelerator IP. This is the IP that we use for our Ultra Plus devices. So let's take a kind of quick look through that diagram. So on the upper left, we have commands and waits entering from either on-chip memory, in the case of small networks, or in the case of larger networks, an external memory such as a SPI flash. On the lower left, we have the activation storage area. So initially, at the start of any operation, this is loaded with input data. And then when we finish processing, this is where we also store the output. And then as we go through the various operations, it's used for intermediate data storage. And on the lower right, we have the different aspects of the actual engine. And again, there are blocks to handle all of the main functions that are typically required, including convolution, scaling, ReLU, pool, and fully connected. So of course, we need to be able to create code to run on those accelerator cores. And what I'm showing on this slide is the various steps that you do as a user in order to achieve that. So there's basically 5 steps that are needed to create code that will run on the device. The first step is to load the network and test images into the compiler tool. So if you're working with TensorFlow, that's a .pd file. And if you're working with Caffe, it's a .proto and a .cafe model file. After you've loaded the network into the tool, there's an option to review that, as I show in box 2. And then we run a step we refer to as the analysis step. So what we do is we take the network and run through it layer by layer and go from the number representation that was used during training. Often that will be a floating point representation, and quantize that to the 16-bit or 8-bit or 1-bit that we use for actual implementation on the device. Then we run through the actual compilation step, and then that's followed by a simulation step. And in the simulation, what we do is we provide an output that shows what the output of the engine would be for the test images provided. If the data had been processed using floating point, and then we provide another output that shows what the output is given the quantization that's been applied. So this is kind of a good cross-check for designers. You can check to see is the tool working correctly, and is the quantization acceptable for that particular design. So before we go through to the next few slides, thought it might be interesting to do another poll. So in this particular poll, we're asking what deep learning framework do you currently use, or if you're not currently using one but plan on using one, please let us know that. So TensorFlow, Caffe, or other. I'm going to be pretty interested to see the results out of this particular poll. So in my observation, as I work with different developers, this seems to be a pretty dynamic area, a lot of change. So it'll be interesting to see, at least for this audience, which tools they prefer to use. Okay, so it looks like TensorFlow is being used by about 55%, about 20% using Caffe, and about 25% of folks using some other framework. Really interesting for us guys here at Lattice, and I'm sure also interesting for you folks in the audience just to see what some of your other colleagues are using out in the industry. So what we've noticed is one of the most challenging aspects to implementing AI or machine learning on device for edge applications is the problem of optimization, because there's a lot of difficult variables that need trading off. We found that the framework that I present on this slide is really quite helpful in terms of thinking about the different variables and thinking about the trade-offs. So let me walk through this a little bit. On the left-hand side, I show things that I would think of as attributes to the implementation or to the end product. So there's power consumption, there's device size, performance is measured in frames per second, the accuracy, and also the ability to detect small objects as measured as a percentage of field of view. And across the top, I show the kind of variables that as developers, you're able to change. So on the device side, you can choose how many engines you want to apply to this, the amount of local memory you want to dedicate to the function. And from a network design side, you get to choose the input size, the complexity of the network that I represent here as the number of multipliers, and then the bit width that I use, the amount of quantization. And where there's a meaningful correlation, I put either a red or a green box in the matrix. Red indicates that as you increase a variable as a developer, has a somewhat negative impact on the attributes of the overall product. And when I show something as green, it shows when you increase a variable, it has a positive impact on that attribute. So let's kind of walk through that a little bit. So as we think about the number of engines, as I increase the number of engines that are used for implementation, power tends to go up. It also requires typically a larger device, so device size increases. But the positive of doing that is performance is measured by frames per second also goes up. In terms of the amount of local memory that I allocate, what we find is as we increase local memory, typically power consumption goes down. The reason for that is there's less need to go to off-chip DRAM in order to implement the function. As I increase memory, device size tends to increase, so that's somewhat negative, but performance also tends to improve because I can minimize the number of accesses to off-chip memory. On the network side, as I increase the input size, what we find is performance tends to degrade somewhat, accuracy improves, and also the ability to detect small objects tends to improve. In terms of the complexity of the network, as I indicate here by the number of multipliers, increasing the number of multipliers tends to reduce the performance in terms of frames per second, but has strong benefits in terms of accuracy. And then as I think about bit widths, as I more heavily quantize, what I see is performance increases and accuracy decreases. So here I'm talking about, I guess, the reverse of quantization or a bit width. So as I increase the bit widths, performance degrades and accuracy improves. So I wanted to make this more real for you folks in the audience. And to do that, I thought it would be helpful to go through some very specific examples. So what I do on this slide is just talk through the basic aspects of the examples that I've chosen. So I've got two basic functions. One is face detection. And in face detection, what we're doing is looking to see, is there a human face present in the image? So this might be used to turn on an electronic device or a piece of mobile electronics. And the second function that we're looking at is what we call human presence detection. So here I'm looking not just for a human face, but a human face or a human body in the image. And you might imagine there's a lot of interesting applications for that. For instance, in security, to see if there are people in the image. Again, maybe for consumer electronics, to see whether someone's in the room, should they have the TV on or the TV off, these kind of functions. And then for each of these two functions, we've looked at two different implementations. You can think of it as a complex implementation and a simple implementation. So if we look at face detect first, on the top row, you see I've got an implementation. It's a VGG style network. It's relatively simple. So the number of multiplications, about 290,000 for each pass through the network. And we're operating on a relatively small network size, 32 by 32, or input size. The second row within face detection is a more complex version of this function. So there we have about 14 million multiplications for each pass through the network. And the input size is 90 by 90. For human presence, you can similarly see I've got a simple example, about 8 million multiplications to get a single pass through the network, and a 64 by 64 input size. And then I have a more complex one with about 338 million multiplications per pass through the network, and an input size of about 128 by 128. So let's take a quick look at how this is implemented on the hardware, and then I'm going to switch gears and share out some results to see how that looks as we run it through the tools. So in this particular slide, what I'm doing is showing the implementation on the left-hand side in our ECP5 product. So you can see I take some data from a camera, I pass that to the ISP engine, and then from the ISP engine, I pass that data into a CNN accelerator. On ECP5, we have a lot of flexibility about how many engines and how much local memory we apply to that problem. Once we have the result from the CNN accelerator, I pass that to what we refer to as the overlay engine. The overlay engine takes the output from the ISP and allows us to place boxes and text on top of it to display the final result. You can also see around the diagram we've got the DDR memory hooking up to the CNN accelerator, and then on the bottom right of the diagram we have a SPI memory, and then there's a SPI to DDR loader. So at boot we take the contents of the SPI memory, which contains the program and the weights, and load that into the DDR memory for execution. On the right-hand side, I show a similar diagram. That's for our Ultra Plus. It's a little bit simpler, so let me quickly talk through that. So you can see, again, we have the camera. We go through a down sample, and then we pass that down sample into the CNN accelerator. Here we use 8 multipliers, and then we can choose how much local memory is being utilized. The output in the case of Ultra Plus typically is a little bit simpler, so normally we'll have one or more signals coming out of the network indicating something's happened. For instance, is there a face present? Is there a person present? Where in the image is the person? So I'm showing that as LED outputs. And then at the bottom of the diagram, you can see we have the SPI memory. And as a reminder, the SPI memory is holding the instructions and the weights associated with the network. So this slide gives you a sense of what the actual hardware that we typically implement on looks like. So on the left-hand side is the hardware we're using for our Ultra Plus devices. We call this our UPduino Shield board. So it's actually a stack up of two boards. The top board has the camera and some LEDs. And then the bottom board has the ICE 40 Ultra Plus device, along with the circuitry necessary to program it via USB. That whole board setup is about 1 inch wide by 2 inches long. So a really pretty small development kit. And then on the right-hand side, we show the kit we most normally use for our ECP5 product. So we refer to this as the Embedded Vision Development Kit. You can see it's a stack up of 3 boards. So the top board has the cameras. So there's actually 2 cameras available for use, although in these examples we just use one. That is then passed to the center board, which has the ECP5 device on. So this particular kit comes with our largest ECP5, the ECP585. And then we have an output board that takes the output, converts it to HDMI, and allows that to be displayed. So let's take a look at how things look in terms of running those networks through the software tool. So we're going to start by taking a look at the face detect implementations. On the left, I show details of the version that had a 32 by 32 input size. The bars on the graph represent the number of cycles needed to implement a pass through the network. And I've divided this into the various operations that are required. So on the left, convolutions are shown in orange, pooling is shown in gray, fully connect is shown as yellow, and then other operations are shown in dark blue. The leftmost bar represents the Ultra Plus device, and then the 3 bars to the right different sizes of ECP5. And the green line translates the number of cycles into frames per second, assuming that we're operating the Ultra Plus at 40 megahertz and the ECP5 at 125 megahertz. So you can see frames per second goes from a few hundred in the case of Ultra Plus up to several thousand in the ECP5. I should note that this is really the processing capability of the FPGA. Of course, in reality, we slow down either to match the input speed of the camera or in some cases to run even slower in order to reduce power consumption. So you can see at the top of each of the bars, I give some indication of the power consumption for the FPGA and the size of the FPGA required in terms of area. So the Ultra Plus solution here runs at 1 milliwatt and is a 5.5 millimeter squared solution. And then you can see the ECP5 solutions range from 0.5 watts to 0.6 watts, sorry, to 0.8 watts, and is 10 by 10 millimeters or 100 millimeters squared. Then on the right, I show some similar information, but for the larger, more complicated network. Overall, the format of the chart is the same, but there are a few differences. First, because this is a larger network, it only fits in the ECP5 devices. So you see there's no bar for the Ultra Plus. And secondly, you'll see there's now some light blue at the bottom of each of the bars, and this represents DRAM access. So this is a larger network, and we're not able to hold all of the intermediate data on chip, particularly as we look at the smaller ECP5 25 device. So you can see there's some cycles required for DRAM access. Overall performance is about 20 frames a second for the smallest device to a little over 100 frames a second for the larger ECP5. So this set of graphs is very similar in terms of format, but it reads out the capabilities when we do the human presence detect functions. So the left-hand side represents the smaller network with a 64 by 64 input, and the right-hand side shows the more complex network. So again, I report out the power consumption and error at the top of the bars, and then the frames per second that's achievable. So you can see on the left-hand side, frames per second, about 10 frames a second for Ultra Plus, going up to a little over 300 for the largest ECP5. If we look at the more complex network, which is with 128 by 128 as the input size, there you can see frames per second, about 20 on the smallest ECP5, the ECP525, going up to, sorry, about 2 frames a second on the smallest, going up to about 5.5 on the largest ECP585. So let's bring all that together and kind of look at how these different results compare. So in this chart, the left-hand column is the different networks, and then in the next column to the right, I show an estimate of the smallest object that can be detected as a percentage of the field of view. So what you can see is as we increase the input size, generally we're able to detect smaller objects as a percentage of field of view. Then for the next 4 columns, I report out the frames per second. So you can see quite a range here, you know, with the most complex network running at about 2.3 frames a second, to the simplest one on the largest device running at over 5,000 frames a second. And then across the top with the column headers, I show the power consumption. So you can see on Ultra Plus, we go between 1 and 7 milliwatts, and then ECP5, 0.5 to 0.8 watts. And you can see the area of those devices as well. So I've got a quick summary of what we've talked about today. As Deepak started out, he talked about some of the challenges relative to AI at the edge and the need to implement that to solve real-world problems. He then went through 3 different examples of how FPGAs might be used at the edge, so standalone, or as an activity gate, or as an accelerator for an MCU. And he also talked through the Sense AI stack and how that really provides all of the building blocks for doing on-device AI at the edge. So, you know, the silicon, the soft IP, the tools, the development boards, and reference designs. And what I hope that I've conveyed in my portion of the presentation is really as a developer using FPGAs, you have a very wide array of configuration options that are available. So the engine size, the bit widths, the network that you choose to implement within the device, and that allows you to span quite a wide range of performance, power, and area. So as I note here, powers between 1 milliwatt and 1 watt, and areas between 5.5 millimeters squared up to 100 millimeters squared. So So I know a lot of you are probably pretty excited to go and check some of this out, do some experimentation on your own. And I wanted to just make you aware of some resources that we have available on the Lattice website. So if you go to latticesemi.com/senseai, you can find a whole variety of resources available that will enable some design exploration. So there's 4 ECP5 based reference designs and demonstrations. So this is the output of Caffe and TensorFlow for examples such as the ones that I went through, along with the VHDL and Verilog to actually make that work on the device. We have also 4 of those for the ICE 40 Ultra Plus devices. These are all available for free download. We have our CNN accelerator IP, which is available for a free evaluation. We have the compact accelerator IP, which is available free of charge. The neural network compiler tool, again, that's free of charge. We've got the embedded vision development kit. That's currently on a $199 promotional price till the end of the year. So if you're thinking about going and getting one of those, now would be a good time to do that. And then the UPduino Shield board that I showed you, the web page is up, and you can go and register your interest. A little later this month, about the middle of November, we're going to have that available for sale. We're still deciding on the exact sale price, but it's going to be somewhere around $49. So in a couple of minutes, we're going to hand off to Brian. Brian's going to talk about a few things from the Embedded Alliance, and then we'll go to Q&A. But before we did that, I thought it'd be interesting to do 2 more polls. So the first poll, we're just kind of interested in the next year. Do you think you're going to use AI or machine learning in your design? Hopefully, some of the presentation today is good inspiration. There's certainly a lot of tools and capabilities out there, and it's a very interesting field. So hopefully, a few of you are thinking about that. Of course, we'd love for you to do that on the Lattice devices, but nonetheless, a really interesting field to go investigate. Okay, so it looks like we got the right people that showed up. About 66% of you are thinking that you're going to do that. We've got a small number that probably not going to do that, and about 28% of folks that are not sure. So I guess we'll have to do another webcast so that we can move you into the yes or the no category. One other poll before I hand it over. Just interested to see from the audience what the FPGA experience is. This is really helpful for me and Deepak as we go through the Q&A with you folks to understand, how many of you folks are actively designing with FPGAs, and perhaps how many of you are considering that but haven't yet used an FPGA. All right, so it looks like about 78% have been using FPGAs before. For about 22% of you, you'd be new to that technology. Really appreciate the input. And as I mentioned, very helpful for Deepak and myself as we answer your Q&A. And with that, I'm going to hand it over to Brian. He's going to say a few words about the Embedded Alliance before we get to that Q&A session.
Thanks, Gordon. As Gordon said, I'd just like to say a few words about the Embedded Vision Alliance, of which Lattice Semiconductor is a member company. The Alliance is a partnership of more than 90 technology suppliers and solutions providers. And our mission is to help developers build better products by incorporating visual intelligence. You can find additional extensive resources focused on practical computer vision technology at the Alliance's website, www.embedded-vision.com, where you can also sign up for our newsletters. Next slide, please, Gordon. Next slide, please. There we go. The Alliance also organizes Embedded Vision Summit events. The next one will take place May 20th through 23rd, 2019 in Santa Clara, California. The summit is the event for innovators who want to bring visual intelligence to their products. It includes multiple days and multiple tracks worth of presentations, along with keynotes from well-known and influential industry members. At the Technology Showcase, top suppliers demonstrate the latest developments in computer vision technologies, and both partial and full day workshops provide opportunities for even more in-depth education. Check out the videos and other materials from the May 2018 Embedded Vision Summit, now published on the Alliance website, and reserve May 20 through 23, 2019 in your calendar. More information on next year's summit, including online registration, will be available soon on the Alliance website. Okay, and now for your questions. I have a number of them already in the queue. Please submit any others you have as we go along. So this first one is a comment and a question both, and it relates to the first survey poll that we did, where the attendees were asked, what is the number one requirement for your on-device AI design? So the comment was, cost wasn't one of the options that was offered in the poll. And for this particular person, that was their number one priority. So for the panelists, can you talk about cost versus alternative implementation approaches, and maybe talk about not only the cost of the FPGA versus the other processor alternative, but also the total solution cost, including any other silicon and other hardware required to implement the design?
Sure, I'll take that. So yeah, I mean, cost is something that obviously is an important criteria as well, especially for AI at the edge, right? On-device AI, like we talked about, usually they ship in high volume. So that is definitely a criteria. And I mean, when we talk about FPGAs, for example, right, there's the cost of the FPGA, but there's also the overall kind of cost savings at a system level, especially when you take into consideration, the flexibility that FPGAs provide, both in terms of, the I/O flexibility to interface to other devices on the board, as well as ability to kind of upgrade to, new algorithms and architectures. So that's definitely, we understand it's an important criteria, and Lattice FPGAs, as hopefully most of you are familiar already, right? Lattice FPGAs have always been optimized for low power and small size and cost. So we do think relative to some of the other options out there, is definitely very competitive.
Okay, great, thanks. Gordon, I think this next one came at the very beginning of your section of the talk. And the question is, can you talk about the difference between floating point and quantized integer, byte, and bit versions of a particular design?
Sure. It's a kind of great question, and actually very relevant as people like to implement AI on embedded devices. So traditionally, as people have been doing AI design targeted more for GPUs and high-end CPUs, typically the networks had been trained and developed using floating point, but quite an amount of industry research and academic research over the last 5 years has indicated that maybe that's a little bit of overkill. And you can get very good results when you use fixed point integer representations of the network, both the weights and the activations. So once you choose to go with a fixed point integer representation, then the question becomes, well, how many bits do I want to use? So common choices currently are 8 and 16. And through our own experimentation, we found in some cases you can even get great results when you quantize all the way down to 1 bit. That's something that often people refer to as a binarized network. More generally, what we've observed is if you train your network using floating point, most normally you can get good results if you quantize down to 16 bits for all the layers, and you may find that there are a few layers where you can further quantize down to 8 bits. If you want to run the whole network at 8 bits, our experience is it's best to train assuming that quantization. And certainly if you go deeper than that, that's even more the case.
Great, thanks, Gordon. Next question. There was a lot of talk in the webinar about CNNs, convolutional neural networks. Is there any current and or planned support for recurrent neural networks at Lattice?
Yeah, so we're certainly looking at a whole variety of other networks other than CNNs. We've got our technology teams looking at what else may make sense. Don't have anything to share or announce today, but I think the message is, like a lot of other people, Lattice is looking at other types of AI beyond CNN. So stay tuned.
Great, thanks. Gordon, I think this next one came in on slide 15, where you were talking about advantages and disadvantages of various implementation approaches. The question is, can you talk about the relative impact of bit width versus power consumption in a design?
Sure. Bit width is kind of interesting in kind of a number of ways relative to power consumption. So obviously, as I reduce the bit width, we find that there's less signals to switch within the device, and that drives somewhat lower power consumption. But at least from our observation, the biggest impact of reducing bit width is it effectively means you can store more words of data in your internal memory. So if I've got a fixed amount of memory, say 2 megabits, and I use 16 bits, I can store a certain amount of information. If I switch to a 8-bit representation, I can store twice as much. That's really important because it reduces the need for off-chip DRAM access. And what we tend to find is that's a large driver in terms of power consumption. So as you have to do more off-chip access, power consumption goes up pretty rapidly. So those are the two factors that we've seen from our side.
Okay, a quick terminology question. For those in attendance who might not know, what is VGG?
Oh, sure. So VGG is a style of network, and I forget what the exact acronym stands for, but there are a set of networks that were developed by the Oxford University Visual Computing Group, and they're fairly common for a whole variety of CNN-type functions, and at least in our experience, are one of the classes of networks that performs quite well in the embedded space.
So more generally, are there any networks you can point to as a good starting point for exploring neural network implementations in Lattice devices?
For sure. I think VGG is an interesting starting point. And I think all the examples that I showed today utilize that as the starting point. Another network that we've used pretty extensively, or group of networks, are those that are referred to as YOLO, or you only look once. So a quick search on Google will find those. Out of the variety of networks that are being published in the YOLO class, the one that we've done the most work with and seems to fit really well is something called Tiny Darknet. And I would recommend that as a starting point, particularly for people that are wanting to identify multiple objects within the image and classify those at the same time. So we've had some quite good success with that particular network.
And speaking of networks, can you talk to current or planned support for custom layers?
So at the moment, most of our focus has been on really, how do we expand out the number of layers that we're supporting that are commonly found in TensorFlow or Caffe, but not yet supported either by our compiler or our IP. As we look out a little bit further in the future, I think custom layers is a pretty interesting area to go investigate. But again, in that area, no immediate plans that I can share out.
How many image sensors does the ECP5 ISP engine support?
So the implementation that we include in the reference design is supporting just one, but the reference design that I shared out, so this is the interface to the image sensor, the ISP that we do, the CNN engine, the DRAM interface, the SPI loader, plus a whole variety of other things. So that fits inside our 25 device. So 85 is 3 times as large. So you can imagine it should be very possible to fit, 3, 4 ISPs within the larger device.
Okay. And then going back to the earlier cost question, why would somebody consider using FPGAs instead of ASICs for implementing AI at the edge?
Yeah, great question. So again, AI at the edge, when we looked at some of the requirements, right, obviously things like cost and power and form factor are usually top the list. But, and again, these are something that you can probably get through ASICs as well. But just given, how early in the game we are with AI, there's definitely a lot of need for flexibility. And again, this is flexibility both at the I/O level to seamlessly interface to existing designs, right? Because that's one of the things designers tell us all the time is as much as we love AI and the potential of AI, we are not going to turn our existing design upside down to accommodate AI, right? So they want this AI accelerator to kind of seamlessly fit in with their existing design. And obviously, FPGAs by nature have a lot more I/O flexibility in addition to the core logic flexibility to adapt to evolving AI algorithms and networks and architectures. So I think that it's a combination of the need for a great deal of this flexibility in addition to the low power. If you look at some of the power consumption numbers we talked about in this presentation, right, we're talking about milliwatts. Usually FPGAs and milliwatts don't get used in the same sentence, right? But with Lattice FPGAs, you can do exactly that. Implement this type of on-device AI in extremely low power and pretty much get the best of both worlds, right? The flexibility of FPGAs with almost ASIC-like power consumption and cost and form factor.
Okay, great questions, everybody. We're unfortunately out of time. I'm sorry we weren't able to get to all of the audience questions today. At the conclusion of this webinar, you'll be invited to complete a very short survey detailing your thoughts about today's event. I strongly encourage you to fill it out so that we can learn how to make future webinars even better. Tomorrow at this same time, you'll receive an email from us explaining how to access a PDF copy of the slide deck we went through today, an archived video of the webinar, and additional information on deep learning for embedded vision and other computer vision topics. So keep an eye out for that in your inbox. Thanks again, everyone, for attending today's webinar, Architecting Always On, Context-Aware, On-Device AI Using Flexible Low-Power FPGAs, presented by Lattice Semiconductor and organized by the Embedded Vision Alliance. Have a good day, everyone.